Hello everyone, my name is Vladimir Khorikov, and the topic of this talk is pragmatic unit testing. So, what's the state of our industry today in terms of unit testing? Well, the state of our industry is that a lot of people know that they need unit tests, a lot of people write them, but the end result is not as good as you would like it to see. So what you often see is that a lot of tests are brittle, not reliable, and don't contribute to the software quality. They are basically a dead weight to the project. And in spite of knowing this, in spite of knowing that a lot of tests in the project hold this project back, many developers still continue down this path, so much that this practice of unit testing becomes cargo cult unit testing. People still write unit tests, however good or bad they are, and just hope for the best. Unfortunately, that's not the best way to approach unit testing. It's very important to not only write unit tests, but also do that in a way that helps your project. And that's what this talk is going to be about. We will discuss what it means to be pragmatic about unit testing, and we will also discuss some unit testing practices that will help you achieve the best return on your effort. A couple of words about myself. So here's my contact information. I blog at enterprisecraftsmanship.com, mostly about enterprise-level application development, about such topics as domain-driven design, functional programming, and of course unit testing. I've authored several courses for Pragmatic site, and here's my Twitter handle. All right, so what's the goal of unit testing? The goal of unit testing, many people think that the goal of unit testing is to improve software design. That is, if you write tests or practice test-driven development, that would automatically lead to better design decisions. And it's true that you can use unit tests to get feedback about your code base. So for example, if you find that your code is hard to unit test, then it's a certain sign of trouble. It means that you need to improve your code. But writing tests in and of itself doesn't automatically lead to better design decisions. If you have some set of tests, that doesn't mean that much. There are too many code bases with good test coverage that are still a mess despite all that coverage. So what's the point then? What's the point in writing all those unit tests? The single most important benefit of having a unit test suite is enabling sustainable growth of your project. Not improving design or anything of that sort. It's making sure that you can sustain the project growth for quite a long time. So that even a couple of years down the road, the developers will still have pretty much the same speed of development as they had at the beginning of the project. A good test suite provides you with a safety net. It provides you with an assurance that you can modify your code base, and this modification will not break any existing functionality. So that you don't have to constantly question yourself, and you don't have to constantly look back. And this gives you a peace of mind. It allows you to move faster, so deliver functionality with a faster pace. And also because you're not afraid of refactoring, you're also able to maintain a low amount of technical debt. This safety net is what allows you to achieve the ultimate goal of unit testing. It allows you to achieve the sustainable growth of your project. You could write application code without tests for a while, and that would even give you some initial performance boost. But as you can see from this diagram, the project growth will eventually decline. So if you don't have tests that constantly verify your code base, that constantly keep it in check, this code base will decay over time. There's no way around it. And so this approach to application development, when you don't write tests, it simply doesn't scale. Sustainability is the key here. You have to plan for the future. You have to think about your code base and structure it and your tests in a way that will help you develop your project in the long run. But it's not enough to just write unit tests. If you have some unit tests, but they are written badly, you still pretty much have the same picture. It's just you're able to defer this point in time when your project enters the phase of stagnation, but nothing really changes in the grand scheme of things. And you might have had this situation in the past, actually. You know, when you start a project from scratch and decide to do everything right this time, and so you write some tests and everything looks good. But after some time, the progress stops anyway. So even with tests, it might take longer for such a project to enter this phase of stagnation, but this phase is still there. 1 year, 2 years max, and the project is basically walking dead. You still may have tests, and you might even run them on each code change, but new features, even some small features, will take like ages to develop, or it may take you a lot of time to stabilize your code base after those new features. And the code base itself might be impossible to refactor because it is too tightly coupled to the implementation details. And so to fix this problem, you will basically need to rewrite all those unit tests from scratch. And so you might think that, well, it's life and there's nothing you can do about it, and that maybe it's normal for a project to slow down after a while. But no, it's not normal. The pace of development does decline over time, but this rate of decline shouldn't be that drastic. It should be much smaller, and you should be able to sustain the project growth for quite a long time. For that, you need to understand the following. Not all tests are created equal. Some of them are valuable and contribute a lot to the software quality. Others, not so. They raise false alarms, they don't catch regressions, they are slow, and they don't provide you with a reliable feedback loop. They're not very useful overall. And in general, it's quite easy to create a test that will have a negative effect on your code base. So not just no effect, but even negative effect when it actively harms your project. So how to evaluate your test suite then? How can you know that your test suite is doing a job and doing it well? Well, what about coverage metrics? If you have 100% code coverage, then everything is fine, right? Well, no. Coverage metrics are not a good indication of the test suite health. And the funny thing is that coverage metrics are a good negative indicator, but they are a bad positive one. So when a coverage metric shows some bad coverage number, say anything less than 50%, then it's a certain sign of trouble. It means that you're not testing enough. Now that's what I mean by a good negative indicator. So they can indicate something negative with your code base pretty well, with a good precision. But the opposite of that is not true. So even if your coverage metrics show some good coverage metric, some good coverage number, that doesn't mean that much. That doesn't mean anything, actually. Even if you have 100% code coverage, you can still have a horrible test suite that doesn't help your project, but instead actively harms it, damages this project. So how to evaluate the test suite then? Unfortunately, the only reliable way to do that is to take all the tests in this test suite and evaluate them one by one. You need to apply your own personal judgment to do that. That doesn't sound plausible because your personal judgment cannot be automated, and it might take you a lot of time to evaluate all your test suite if you have quite a few of tests in it. But there is no other way. There is no automated way to see how bad or good your test suite is. And so the pragmatic approach to unit testing boils down to this. You need to figure out the net value of a test, and by net value I mean the difference between the benefits it provides you with and the maintenance costs. So first step is to figure out the net value and then decide to either keep this test or get rid of it. So sounds simple, right? Problem solved. Of course not. That doesn't help that much. And the question now is how to evaluate an individual test. So let's see. What makes a test valuable? There are 4 components of a valuable test: protection against regressions, resistance to refactoring, fast feedback, and maintainability. And these 4 components provide you with a universal frame of reference that you can use to evaluate any test in your test suite. So let's discuss each of them separately. The first one is protection against regressions. A regression is a software bug. It's a bug in an already existing functionality, and it usually takes place when you add a new feature. So in order to do that, you modify some existing code base, and this modification breaks an unrelated functionality, something that you have already tested and shipped in a previous version. So that's a definition of regression. It's just a software bug. So regressions are annoying, to say the least, but that's not the worst part about regressions. The worst part about them is that the more code you have and the more features you develop, the more chances there are that you will introduce a bug in one of those features. That's because with more code, you kind of extend the surface area for potential bugs. And so to enable sustainable growth of your project, it becomes crucial to develop a good protection against regressions, because without it, you will not be able to sustain it. You will be stuck fixing all those bugs that will constantly come up. And this metric itself basically depends on the amount of code that gets executed during a test. So the more code gets executed, the more chances there are that the test will find a regression. And it's not only about the amount of code, but also about the significance of that code. So, for example, business logic is much more important than some boilerplate code, and so you need to take this into account as well. And also, it's not only your code that matters here, but also the code that you didn't write. So, for example, code of the external libraries or frameworks that you use in your project. And so, generally, to maximize this metric, you need to aim at verifying as much code as possible in your project, in your test suite. And on the flip side, testing trivial code is not worth it, because it's too trivial. It doesn't contain a substantial amount of business logic. All right, that was the first one, the first component. The second component is resistance to refactoring. So picture this situation. You wrote a feature and everything is good. So the feature itself is working and all the tests are passing. And now you decide to refactor your code, and so you do some refactorings here, some modifications there, and now everything looks even better than before. Except one thing. Now the tests are failing. And so you decide to look closer to see what exactly you broke with your refactoring, but it turns out that you broke nothing. Everything works just fine, just as before. It's just the tests were written in such a way that they break with any modification of the underlying code base. And they do that regardless of whether you actually break the functionality or not. This is called a false positive. A false positive is a false alarm. It is a result that indicates that a test fails, whereas the functionality it covers is working just fine. Such false positives usually take place when you refactor your code base. That's why I call this component resistance to refactoring. And so they usually take place when you modify the implementation details but keep the observable behavior of the feature intact. Developers rarely think that false positives are important, and they usually focus on the first component, on protection against regressions. But false positives actually can have a devastating effect on your entire test suite. That's because they dilute your ability to quickly spot a problem in code. Over time, you sort of get accustomed to test failures. You get used to the fact that your tests fail with no good reason. And so after some time, you stop paying as much attention to them as before. And you also stop paying as much attention to legitimate failures too. So you start ignoring legitimate failures with all those false alarms. And that leads to losing trust in your code base, in your test suite. And that's not a good situation, because you need to perceive your test suite as a reliable feedback mechanism, as a reliable safety net. And false alarms diminish this perception. So what causes a false positive? The amount of false positives you get is directly related to the way you structure your tests. So the more you couple your tests to the code implementation details, the more false positives they will produce, the more false alarms they will generate. And the only way to avoid that is to decouple your tests from those implementation details as much as possible. So basically, you need to verify the end result of your code, not the actual steps it took it to produce that end result. And without such decoupling, you will have all those test failures with each refactoring, regardless of whether you actually break the functionality or not. You will still have those test failures. Note that not all false positives are equally harmful. Some of them are actually not that bad. For example, if you add parameter to a method under test, that usually leads to compilation errors, and they are not that bad because they are quite easy to fix. You just follow the compiler and fix any place in the code that it points to. The worst type of false positives are those that seem as though they point to legitimate failures, because those are the hardest to deal with. So here they are, the first two components of available test, protection against regressions and resistance to refactoring. Let's look at them from another perspective. So here is a diagram, 2x2 table, and it shows two possible states of a test and two possible states of the functionality this test covers. So the test itself can either pass or fail, that would be the rows of this table, and the functionality can be either, so it can work either correctly or incorrectly. It can be either correct or broken. That would be the columns of this table. When the test passes and the functionality itself is correct, we say that it is a correct inference. And also when the test fails and the functionality is broken, we also say that it is a correct inference, because we do expect our test to fail when the functionality doesn't work. That would be a true positive. But when the test fails to catch an error, that becomes a problem. And that is a type 2 error. And that is what the first component helps us deal with. It helps us deal with false negatives, basically with bugs. And also we have a symmetric situation when the test fails, but the functionality itself is correct. And that is what the second component helps us deal with. So it helps us deal with type 1 errors, false positives. So again, protection against regressions help us deal with type 2 errors, false negatives, and resistance to refactoring helps us deal with type 1 errors. All right, so here they are, and there are two more components. The fast feedback is pretty much self-explanatory. It's important to get fast feedback, because the faster you see a problem in code, the quicker you will be able to fix this problem, and the less expensive the fix would be. And the only way to get this fast feedback is if your test suite is executing quickly enough. And the fourth component is maintainability. It's maintenance costs. So it's basically a metric of how hard it is to understand and maintain your tests. And this metric basically depends on just a number of lines that it took you to write the test. The smaller the test itself, the easier it is to understand this test. And these four components, when multiplied together, they provide you with a value estimate of a test. And by multiplied, I mean in a mathematical sense. So in order for a test to be valuable, it needs to score at least something in all four components. And if it scores 0 in one of the components, then its overall value turns to 0 as well. That's what I mean by multiplied. So, and this approach is universal. You can apply it, as I said, you can apply it to any test in your test suite, and it will provide you with a rough value estimate of your test. And then you will be able to decide as to keep this test, refactor it, or get rid of it. The most interesting thing about these components is that the first three of them, the first 3 out of 4, are mutually dependent. They are mutually exclusive. And it's impossible to maximize all 3. You will have to sacrifice one of them in order to maximize the other 2. So let's take some examples. We will start with end-to-end tests. End-to-end tests are tests that verify your application end-to-end. They verify everything, including the UI, the code base, the database, and probably even some external services that your project uses. End-to-end tests provides the best protection against regressions. That's because they go through a lot of code when executing. That code includes, obviously, your code, but also the code that you didn't write, the code of the external libraries and frameworks. End-to-end tests are also mostly immune to false positives, because if you do a refactoring correctly, that refactoring doesn't affect the observable behavior of the system, and thus they don't affect this refactoring doesn't affect the end-to-end tests, because end-to-end tests view your system from the end user's point of view. They don't care about the implementation details of your system. So, but despite this fact, despite these two benefits, end-to-end tests have a major drawback. They are slow, like really slow. If you have only end-to-end tests in your test suite, then you will have a hard time getting rapid feedback out of your test suite. And that is a deal breaker for most teams, because, because it's important to get rapid feedback. And that is why it's pretty much impossible to have only end-to-end tests in your test suite. So if we go back to this diagram, we can put end-to-end tests to this intersection. They have a good protection against regressions. They have good resistance to refactoring, but the component they lack is the speed. They are slow. Next, we have trivial tests. A trivial test is a test that covers some simple piece of code, and piece of code that is too simple to break. And so you can see an example here. On the left, you can see a user class with just a simple name property, and on the right, you can see a test that sets some string to this name property and then verifies that that this property contains the correct value. Unlike end-to-end tests, these tests do provide fast feedback because they can be executed really quickly. And also, they have a fairly low chance of producing a false positive. So they have a good resistance to refactoring. But the problem with them is that they are unlikely to catch any regression error, just because the underlying code is too simple and there is nothing to break in there. So if we go back to our diagram, we can put trivial tests here into this intersection. They are fast, they have a good resistance to refactoring, but they don't provide you with a good protection against regressions. And finally, there is the third bucket, and that is brittle tests. Similarly to trivial tests, it's pretty easy to come up with a test that will execute fast and will have a good protection against regressions, but will do that with a lot of false positives. And you can see an example here. On the left, there is a user repository that gets a user by some ID, and it also saves the last executed statement, SQL statement, to some public property. And on the right, you can see a test that verifies this behavior. So it verifies that the last executed SQL statement is correct. So this test will catch a regression error because, well, for example, a developer can mess up with the SQL and accidentally put, say, customer instead of user. And this test will reveal this error, so it will catch it. But does this test have a good resistance to refactoring? What do you think? No, absolutely not. So here are different variations of the SQL statement that leads to the same result. And if you change the SQL statement in the user repository to any of these variations, the test will still raise an error, even though the functionality itself wouldn't be broken. It will work perfectly fine. And the reason why the test produces a lot of false positives is because it is tightly coupled to implementation details of the system under test. There are several ways the repository can solve this problem, but the test insists on a particular one of them. So what we have here is, in essence, the test copies the implementation from the user repository to itself, and it breaks if you modify this implementation. It doesn't verify the observable behavior of the system under test. So going back to our diagram, we can put brittle tests here. So they execute fast, they have good protection against regressions, but they do that with a lot of false positives. So they don't have a good protection against good resistance to refactoring. As you can see, it's quite easy to come up with a test that will maximize 2 out of 3 components at the expense of the third one. And this test will still have a close to 0 value. That's because of the multiplication rule, because remember, in order for a test to be valuable, it needs to score at least something in all components of a valuable test. And because of that, because of this mutual exclusiveness, it's quite hard to keep a balance here. It's quite hard to keep a balance between these components. Anything less than end-to-end tests will be prone to refactoring to some degree. And at the same time, if you want to get a good protection against regressions, you need to cover a lot of your code base with unit tests. But it's pretty much impossible to do without knowing at least some implementation details of your code. And so here, this ideal here in the intersection between the 3 components, it's impossible to reach, unfortunately. But it's still possible to get your tests quite close to this ideal. Not exactly in the intersection, not exactly in the center, but still quite close. So now that you are familiar with this new frame of reference, you can view a lot of existing paradigms in a new light. So let's take test pyramid, for example. Test pyramid consists of 3 types of tests: unit, integration, and end-to-end. And the concept of pyramid itself is it's just about the ratio in which these types of tests appear in the test suite. So because unit tests are they are fast, it makes sense to have more of them. And on the other hand, end-to-end tests are the minority because they take a lot of time to execute. And so tests residing on each level, they have different value proposition. The higher the level, the more protection against regressions you will get and the more resistance to refactoring you will get, but you will do that at the expense of feedback speed. On the other hand, the lower the level, the faster your tests will execute, but at the expense of protection against regressions and resistance to refactoring. So as you can see, nothing comes free. Everything comes at a cost. All right, let's now talk about different types of unit testing. So just like tests are not equal in their contribution to the software quality, not all types of unit testing provide equal results. There are 3 major types of unit testing. The first one is output-based testing. It's when you supply some input into the system and then verify what comes out of it. And the yellow line here on this diagram shows at which point we do the assertion. So here we assert, we verify the outcome of the system, we verify what comes out of it. And to apply this type of unit testing, the system under test itself shouldn't modify any internal or external state, so that the only component to verify would be its output. And here's an example. So on the left you can see a price engine that takes an array of products as an input parameter and then generates some discount. And on the right you can see a test that generates a couple of products, it supplies them to the engine and then verifies that this engine generates the correct discount. So this system under test here doesn't leave any side effects and it doesn't refer to external world. So we can say that it is purely functional because it fully encodes its inputs and outputs into its method signature. The second type of unit testing is state-based testing. So here you verify the state of the system after the operation is completed. So you provide some input into the system, its internal state shuffles around and ends up in some final state. And you would then verify this final state with your tests. And here's an example. On the left there is a simple order class with a list of products, and it allows you to add a new product to this list. And on the right you can see a test that adds a product to the order and then verifies that this product exists in the collection of products within the order. All right, and the third type is collaboration-based testing. So here you focus on collaborations between the system under test and its neighbors. You check that the system under test calls correct methods on the collaborators. It does it with correct parameters and in the correct order. And to do that, you usually substitute the collaborators with test doubles, such as, for example, mocks. Here's an example. On the left, there is an order service that submits an order to the database, and on the right, there is a test that verifies this behavior. So it creates an order, mocks the iDatabase interface, and then verifies that the order service calls the save method on this interface. All right. So here are the 3 types of unit testing and the 4 components of available test. And let's compare now these types of unit testing using our new frame of reference, using our 4 components. So if we're talking about unit tests, tests that don't refer to any out-of-process dependencies, then all 3 types of testing they generate tests that execute fast. So because they don't touch anything, database, file system, anything out of process. And if you don't use them to cover trivial functionality, then they also have a high chance of catching a regression. So the first component is on par here as well within these 3 types of unit testing. But the second and the fourth component differ quite significantly. Let's discuss them in more detail. The output-based testing provides the best protection against false positives. Of all unit tests, tests written in a functional way have the best resistance to refactoring. That's because among all parts of the SOT, of the system under test, its API, so its inputs and outputs, they usually change less frequently when you do the refactoring. And if they do, it usually leads to compilation errors, and they are quite easy to fix. And so normally you can modify the internal implementation of the SAT completely, and the tests written in a functional way will not raise any false alarms. That's of course given that the API signature stays in place. These tests are also easier to maintain usually because they are short and concise. And by the way, that's no coincidence because the functional style of unit testing boils down to just two things. You provide the input into the system and then verify the output, and that's it. And it doesn't take you a lot of code to do that. The drawback here, the drawback of this output-based testing is that it is only applicable to code that itself is written in a functional way. So, and unfortunately, it's not possible to write all your code in such a way, especially if you use some object-oriented programming language like C#. The second type of testing, state-based testing, it is more prone to false positives, but it's still good enough. And you just need to make sure that you verify the API of the system under test and don't expose any implementation details of the system under test. You don't violate its encapsulation. For that, you need to make sure that, well, you need to think carefully about what parts of the SAT you expose publicly. So you shouldn't reveal the implementation details. And that means that you need to, well, your tests basically need to copy the behavior of the production code. They should act exactly as production code. And they shouldn't have any special privileges. And so as long as the SAT's encapsulation is not violated, state-based testing is close enough to output-based testing. It's still unlikely to produce false positives, and the maintenance costs of such tests are not that high. So the assertion part tends to be bigger because you might have a lot of state to verify, but it's usually manageable as well. And with the collaboration-based testing, the situation is more complicated. So, first of all, the maintainability of such tests is usually worse. That's because you often need to maintain a quite complicated mock machinery in order to do the assertions. And all those mocks, they take a lot of space and they don't help with the test readability. And second, resistance to refactoring or protection against false positives, it can be much worse. And that's because the collaboration-based testing, it tends to couple your tests to implementation details of the SAT. There's more nuance than that, actually. So remember, we discussed that the false positives are usually a result of coupling tests to implementation details. And so to avoid that, you need to decouple your tests from those implementation details as much as possible and instead verify the observable behavior of your system. So let's discuss what that means exactly. So let's take a typical enterprise-level application and represent it in a hexagonal form. At the core of it, there is domain model or business logic. That's basically the same thing. Outer layer here represents the application services layer. And that layer coordinates the work between the domain model and the external world. So it sits on top of the domain model. And the application itself can talk to multiple external applications. For example, message bus, third-party systems, or an SMTP service. So, what would be the observable behavior of such a system? So, the observable behavior of any piece of code is, by definition, the behavior that its clients can observe. So let's take the domain model, for example. Who is the client of this model? Well, it's application services layer. And so the observable behavior of the domain model would be the things that the application services layer can see and work with. So that would be the domain model's public API. And now the question to you, what would be the observable behavior of the application services layer, the layer that sits on top of the domain model? What do you think? Well, because the application services layer communicates with the external world, its observable behavior would be the way it communicates with that world. So the things that the outer world can observe. So, for example, the way it reacts to stimulus from the external applications or the messages it sends to them. So that would be its observable behavior. And so in any application, there are two types of communications: inner application and inter-application communications. Communications inside the application and communications between the applications. Communications inside your application are implementation details. That's because the collaborations between classes inside your domain model, they are not visible from the outside of that domain model, and so they don't comprise the public API. And so you need to avoid coupling your tests to these kind of collaborations, because that would lead to fragile tests. That would lead to tests that will produce a lot of false positives. But communications between applications is a different matter. So unlike communications inside applications, the way your application talks to outside world does comprise its public API. So you can say that it is part of its contract, it's part of its post conditions. This distinction stems from the way different applications evolve together. So one of the main principles of such an evolution is maintaining backward compatibility. Regardless of how many refactorings you do, the way your application talks to external applications should always remain the same, so that the other applications can still understand it. For example, if you work with a message bus, the messages, or rather the structure of the messages that your application puts on that bus, it always should stay the same, so that the other application can still parse them. Or let's say that you work with a payment gateway. Then, regardless of how many refactorings you do, your application should still call the same URL within that payment gateway and with the same payload, so that you always charge the same amount of money within the same use case. So, and collaboration-based testing can be beneficial here because it allows you to do exactly that. It allows you to verify the communication pattern between your application and external applications. And the tests that you will get as a result, they don't couple to implementation details because this type of communication is observable from the outside world and it does comprise the application's public API. So, right, but this is not the case for communications inside the application. And this difference between inner application and inter application, it is crucial. It's very important. So it is one of the main reasons why people fail at unit testing. They often build these complicated mock machineries and start applying it to everything, to communications between applications, communications inside the application, to everything. But mocks can they have only a restricted area of applicability, and that is verifying the communications between your application and external applications. And that's it. If you use them for anything else, you are doing it wrong. So let's take some examples. Here on the left, you can see an order class that, while adding a product, it notifies the user that it needs to update its last bought product. And on the right, you can see a test that verifies this behavior. So it verifies that the order calls this update last bought product method on the user. And this is an example of a fragile test, because communication between the order and the user domain classes, it is not observed from the outside of the domain model, and so it is not part of its public API. And verifying this communication leads to coupling your tests to implementation details. So what you get here essentially is the situation when those implementation details are now set in stone, so to speak, and any attempt to refactor those details will lead to test failures. So in other words, your tests now, this test doesn't have a good protection, good resistance to refactoring, because that's a collaboration inside the application. And here's another example. On the left, there is this order service that has an iPayment gateway interface as a dependency. And on the right, there is a test that verifies that when the order service submits a payment, it charges the client the correct amount of money. And this payment service is an external application. And so the call that your system makes to that external application is a side effect that is visible from the outside world. And so coupling to this side effect will not produce fragile tests, because unlike the example with the user and the order, you do want to make sure that this type of communication stays in place, even after you refactor your code base. And so the collaboration-based testing is justified in this case, because it is a collaboration between applications. So here how we can display these two types of communications on a diagram. As you can see, the call between the domain classes, between the user and order domain classes, resides inside the domain model. And so it is an implementation detail. But the call to charge payment goes to another application, and so it is not an internal implementation detail. So that's an important difference between these types of communications. All right, so to summarize these three types of unit testing, the most valuable one is output-based testing. So tests written in a functional way are the most valuable asset in your test suite. If they cover non-trivial amount of code, they give you a good protection against regressions. And also they produce the least amount of false positives among all unit tests. So the only kind of tests that produce even fewer false positives is integration or end-to-end tests. The problem with them is that it's rarely possible to have only these kind of unit tests in your test suite because, as I said, the underlying code itself should also be written in a functional way. It shouldn't have any side effects, and it's impossible to have only functional code in your code base. But still, it's a good idea to adhere to this style of unit testing as much as possible, wherever you can. State-based testing is the second best approach, the second best choice in many cases. But you need to just make sure that you verify the public API of the system under test and you don't expose any implementation details of the system under test. So, for example, you shouldn't make state public that would otherwise remain private. So you shouldn't do that just for the sake of unit testing. And finally, collaboration-based testing is good when you verify collaborations between applications, between your application and external applications, but it is bad when you verify collaborations inside the application, inside the domain model. The general guideline here is this. The further away you take your tests from the implementation details, the better. And what it means is that you need to verify the end result, the observable behavior of the system under test, and not its internal implementation details. All right, so as you might guess, the most important takeaway from this talk is this difference between inner and inter-application communications. Not because it's difficult or particularly hard to understand, it's just many developers don't make this distinction. But at the same time, like I said, this distinction is crucial for your tests. It can make or break your entire test suite. And so I'd like to give you an example here. This example is from the book Growing Object-Oriented Software Guided by Tests. It's a very good book overall, and it provides you with a good insights in the topic of unit testing and the topic of test-driven development in particular. So really recommend this book. But even this book doesn't make this distinction between the two types of communication. And so I'd like to show you the sample project from this book, the initial version of this sample project, and the version that you can get after refactoring. The sample project itself is written in Java, and so I rewrote it in C#. It's not a 100% line-to-line rewrite, but it's pretty close. And on this diagram, you can see a gist of its structure. The application itself is an automated bidder for auction items, so for items that are being sold on an auction. In the center of this diagram, there is a buyer class. It is the main domain class in this application. It makes decisions as to either pass on an item or make a bid on it. The second main class here is warehouse. It's where the information about new auction items come from. And when this information takes place, this warehouse class, it calls stack item. This stack item then calls stack message translator, and this translator calls the buyer. So I'm just giving you some overview here. And the buyer itself can call the stack item when it decides to bid on an item, and it also calls this main view model when it updates its internal state. So I know that that kind of sounds complicated, but don't worry, it's not that complicated. This main view model is a class that is responsible for communicating with the user. So it accepts commands from the UI and updates this UI when it gets notifications from the buyer. So that's it. No more descriptions. All right, so we can put these classes into three categories. The category on the left are the classes that communicate with an auction. So they talk with an auction, and the classes on the left. The classes on the right are well, basically the single class on the right is the class that communicates with the user, and in the middle you can see the main model that communicates with classes from both the left and the right. Now, to the issues of this solution. The first issue here is that there are quite a few classes here. You don't need that many classes to implement this solution because this solution itself is quite simple. And this issue is direct consequence of using the collaboration-based approach, the collaboration-based unit testing. Because the collaboration-based unit testing encourages you to represent the business logic as a set of communications between classes in your code base. And so that, in turn, encourages you to have more of such classes. And because you want to represent each individual communication separately, and you cannot do that with just a couple of classes. You have to introduce more of them. The second problem here is that this solution doesn't make a distinction between different types of communication. So, for example, the call from stack item to stack message translator is an example of a call that comes from the outside world. So it comes from an auction. And the call from stack message translator to the buyer is an example of communication that takes place inside the domain model. At the same time, tests verify these two types of communications in the same way. So here you can see an example. So here, the test instantiates a translator. It also passes event close message to this translator and then verifies that this class calls this item closed event on the buyer. And this is an example of coupling the test to the SOTS implementation detail. Because if we put these two types of communications on the diagram, here's what we will get. So the message from the auction to our system, this event close message, is an example of an external communication that comes from the external world. And the result of this message is this method call that happens between the main classes. So this item closed method call from translator to the buyer. And that is an internal implementation detail that you shouldn't verify with your tests. So what's the alternative here? How can we refactor it? So the alternative here is to represent the buyer as a state machine that accepts events from the auction and then generates some commands. And this command then will go back to the auction and will bid on separate items. So here how the overall architecture will look like. Again, I don't want to dive too deep into this here, but just to give you some overall overview. So on the bottom, so we now have the domain model on the bottom here, and all the communications now go inwards in the domain model, so to the domain model. The domain model itself now doesn't communicate with the auction or with the user. And this communication is now a responsibility of a separate application services layer, this buyer view model class. And here's how we can refactor the test. So this is the initial version of the test. Again, what it does is it passes this event close message to the translator and then verifies that this translator calls the item closed method on the buyer. This is the initial version. And this is the final version. So here the test creates a buyer in some particular state, then passes an event to this buyer, and then checks checks the resulting command and checks the state of this buyer. So in this particular case, we don't expect that the buyer will react to the closure of the auction, because we don't expect it to send any messages back to auction when the auction closes. And also the state of the buyer should transition to closed as well. So here what we did is we transitioned our test from the use of collaboration-based testing to the use of output-based and state-based testing. So now we don't verify the implementation details of the SOT and instead use its public API to do that. So that's just one example of a test that we refactored, and I have an in-depth analysis of this initial version and the alternative version in my blog post, and this is the first link here. The other two links are some thoughts about when to use mocks and about how to do that properly. So basically you need to verify the collaborations at the edges of the system as far to them as possible. All right, so let's summarize. The components of available tests. So we discussed the components. They are protection against regressions, resistance to refactoring, fast feedback, and maintainability. And together they provide you with a universal frame of reference that you can use to analyze any test in your test suite. And also we discussed 3 types of unit testing: output-based, state-based, and collaboration-based testing. The most important, the most valuable of which is output-based testing. We also discussed the observable behavior, the difference between the observable behavior and implementation details, and we discussed when to use mocks. So you need to use them to verify collaborations between applications, but not inside applications. All right, that's all I have. Thank you.
А если есть какие-то вопросы, вы можете спросить.
Спасибо большое за презентацию, очень интересно было. А вот у вас там был слайд, на котором было показано, ну и вы рассказывали про то, как в системе, где много тестов, считать метрики и избавиться от ненужных, да, то есть вычленить те, которые не нужны, которые там, не вносят какую-то ценность. А вот можете ли вы дать какие-то рекомендации по процессу обратного, то есть когда есть проект, в котором вообще нет тестов, ну это зачастую какие-то стартапы, да, которые не имеют изначально там достаточно ресурсов для того, чтобы писать тесты, да, и вот какие-то рекомендации по тому, как начать писать тесты, как отобрать те тесты, которые вот нужны будут, как какие-то, может быть, из своей практики.
Это сложно, это сложно.
Да, это сложно, поэтому я спрашиваю.
Отдельно, ну, я к тому, что это сложно писать вот в течение даже 7 минут. Есть отдельная книжка на эту тему Майкла Fathers, Working with Legacy Systems. Вот. Она дает хорошие начальные входные вот рекомендации по тому, как это делать. Вот. Но вообще, если проект был написан таким образом, что у него сильный coupling between different components, sorry,
Okay.
В общем, high coupling between different components. Если проект был изначально так написан, то довольно сложно потом сделать так, чтобы просто на него написать тесты без рефакторинга. То есть вам придется, скорее всего, переписывать какую-то часть этого проекта, ну, как минимум какую-то часть, возможно, вообще весь код. Потому что, когда нет тестов, то ничто вас не ограничивает в том, чтобы написать такой вот спагетти-код. Вот, и поэтому тут очень сильно разнится подход в зависимости от того, насколько хорош ваш код был изначально до этого. То есть, если код более-менее хороший, то вы можете просто написать тесты, ну и, собственно, будет работать более-менее. Вот, если код плохой, то здесь подход может быть, я имею в виду юнит-тест написать в первом случае. Во втором случае, если код плохой, то вам придется, скорее всего, начинать с end-to-end тестов, потому что другие тесты у вас не получится написать. Вот, и потом, после того, как у вас будет кое-какое покрытие, как минимум кое-какое покрытие этими end-to-end тестами, вы уже начинаете рефакторить ваш код. Вот, и с этим рефакторингом добавляются уже юнит-тесты. Вот, я бы так подошел.
Спасибо.
Спасибо за доклад. Такой вопрос вот по поводу того, как найти баланс с тестами. Вот если представить типичное как раз enterprise приложение, которое использует какой-нибудь heavy orm, типа entity framework, Hibernate, и буквально каждая операция — это операция, которая в конечном счете отражается в базу данных, то вот как правильно заходить с тестами в приложение? Получается, если мы тестим с уровня домена, то это не тестирование через Public API, это тестирование каких-то вот атомарных операций. И от него не возникает ощущение того, что мы действительно протестили все. Если мы тестируем с уровня, который уже мы зацепляем Data Access Layer, то тут возникает другая проблема, что вот эти heavy orm, их достаточно трудно закрыть каким-то моком, который действительно заменяет реализацию. То есть, даже вот моки, которые написаны как отдельные библиотеки, они не отражают действительно всю сложность орма. А если мы пишем какую-то свою in-memory реализацию, то iQueryable просто протекает настолько, что мы не можем написать адекватную замену. И мы, если пытаемся мокать, то мы все равно очень важную часть приложения выносим за рамки тестов. Вот то, что вы говорили, чем больше кода мы запускаем тестом, тем лучше. Если мы не запускаем ORM, то мы теряем кучу особенностей поведения. У того же Entity Framework их просто десяток примеров можно прям сходу привести.
Да.
А если мы тестируем на реальной базе, то мы получаем тогда тяжелый тест-сьют, который выполняется долго, со всеми вытекающими. И вот как вот этот баланс найти? Может, у вас есть какой-то опыт?
Да, большой опыт в этом. В общем, я рекомендую так подходить. То есть оба типа тестов нужны. То есть вам нужны и интеграционные тесты, которые будут зацеплять и ORM, и базу данных вместе. Таких тестов, естественно, будет меньше тест-пирамид. И вам нужны юнит-тесты. Юнит-тесты нужно делать на доменную модель, которая работает в изоляции от всего остального мира. То есть вчера были доклады хорошие по ДДД. Нужно доменную модель строить таким образом, чтобы она была как можно более изолирована from the outside world. И таким образом вы сможете ее протестировать отдельно. То есть не нужно будет тогда намокать ничего, просто тестируйте ее как нечто отдельно изолированное. Это раз. То есть, во-первых, юнит-тесты должны быть на доменную модель, то есть заход самой доменной модели. И во-вторых, да, вы правы, что без интеграционных тестов сложно достичь достаточно хороший confidence, потому что у вас не будет уверенности в том, что ваше приложение работает достаточно хорошо. И поэтому интеграционные тесты тоже нужны. То есть те тесты, которые работают и с ORM-кой, и с базой данных. То есть здесь я бы не рекомендовал мокать ничего вообще. То есть либо тестируете доменную модель, которая и так уже изолирована, ее не нужно мокать, либо тестируете все вместе. Тогда тоже ничего не нужно мокать, потому что вы тестируете вместе с базой данных и с ORM. И это, как правило, дает наилучший баланс.
Спасибо. И тогда другой вопрос получается. Если приложение, которое, в общем-то, я к таким же выводам пришел изначально, но если приложение, в нем буквально все операции, они работают через базу, то мы получаем два набора тестов, которые во многом повторяют друг друга. Просто один через уровень дал это делает,
если у вас,
уже ниже.
Да, если у вас доменная модель простая, и там никакое особое ветвление по логике нету, если там все просто, цикломатическая комплексити тоже маленькая, то нет смысла писать тогда домены, нет смысла писать особо юнит-тесты. На такую конкретно, на такую область предметную стоит просто написать интеграционные тесты и все.
А какие-то тогда варианты, как время запуска сжимать? То есть у нас как раз проект подошел к той фазе, когда время запуска 1500 тестов 15 минут. Это уже достаточно критично получается. И как масштабироваться дальше, просто не знаем.
Тут разные варианты возможны. То есть, во-первых, нужно локальную базу всем девелоперам, если еще нету, чтобы каждый на своей локально запускал, не считая CI деплоймента. И, возможно, придется разбить проект. То есть, если 1500 тестов, то это говорит о том, что проект уже, скорее всего, большой и надо разбивать. То есть, как минимум, чтобы это был, возможно, не микросервисы, но один проект монолитный, но при этом, чтобы были в нем разные выделенные bounded contexts. И для них тогда вы уже с ними будете работать отдельно, с отдельным solution, с одним bounded контекстом, с другим, и для них будут отдельные тесты.
То есть тесты по группам просто запускать?
Да.
Понял, спасибо большое.